In elementary biology, we often visualize enzymes through the lock and key model. This framework assumes that substrates and proteins are perfectly rigid, complementary shapes that achieve a fixed, unyielding geometric fit. A static geometric fit fails to explain the physics of actual catalysis. If a substrate simply binds to a rigid mold and reaches a comfortable energy minimum, it becomes trapped in a stable state rather than reacting. This presents a physical paradox. If biological catalysts are not simply catching and aligning substrates, we must identify the invisible forces they manipulate to accelerate metabolic reactions millions of times over. To understand enzyme function, we have to look past shape-matching analogies and analyze them mathematically as dynamic thermodynamic scaffolds that actively distort molecular bonds. Unpacking this mechanism requires three pillars of physical chemistry: the Arrhenius equation, transition state theory, and thermodynamic equilibrium. By applying these principles, we can map exactly how a structural shift in a single protein dictates the precise velocity of a macroscopic metabolic pathway. Enzymes solve a specific biological problem. They bypass strict kinetic bottlenecks to drive exponential speed, entirely within the absolute limits of thermodynamics. Chemical kinetics is governed by the Arrhenius equation, calculating the rate constant K via the negative exponent containing EA, the activation energy. Graphing rate against activation energy visualizes this. Shifting activation energy slightly lower triggers a massive upward spike in reaction rate. The biological consequence here is that an enzyme does not add speed to a system linearly. Cutting an energy barrier in half can multiply the reaction rate by a factor of 1,000,000. The true power of an enzyme is its ability to shrink this specific variable, leveraging the mathematics of nonlinear scaling to accelerate life-sustaining reactions. Activation energy defines the specific threshold of kinetic energy required for two molecules to collide with enough force to break their existing internal bonds. Transition state theory focuses on the absolute peak of this energy barrier. This represents the activated complex, an unstable intermediate state where initial bonds break and new bonds form. This exact altitude from the baseline is the Gibbs free energy of activation. Because this altitude requires a high concentration of energy, statistically, very few uncatalyzed molecular collisions possess the raw velocity necessary to survive the climb and successfully form the complex. Here, the enzyme's mechanical action intervenes via induced fit. Upon collision, the massive protein structure dynamically contorts, wrapping physically around the smaller molecule. Crucially, the active site does not morph to match the initial, stable substrate. It reshapes itself to perfectly complement the distorted geometry of the highly unstable transition state. As the enzyme's amino acids form temporary bonds with the transition state, they release binding energy as enthalpy. This released enthalpy offsets the reaction's energy cost, literally dragging the energy curve's peak downward to a new maximum altitude. By generating binding energy precisely when the molecule is most unstable, the enzyme physically pays a substantial portion of the activation cost. This mechanical stabilization is the exact mechanism that shrinks the activation energy variable in the Arrhenius equation. Zooming out to the full reaction coordinate diagram reveals the contrast between the uncatalyzed and catalyzed pathways. Despite changes in the middle of the journey, initial reactant and final product energies remain firmly anchored. Enzymes are powerless to alter these start and end states. Because these energy states are fixed, the overall thermodynamic equilibrium constant of the reaction remains completely unaltered by the presence of the catalyst. The enzyme accelerates the forward and reverse reactions equally. It does not push a reaction to create more product, it simply drives the system to its natural end state faster. Enzymes are biological machines optimized to clear kinetic roadblocks. By using induced fit mechanics to stabilize activated complexes, they minimize the activation energy exponent and massively accelerate life-sustaining reactions, all while strictly bowing to the immovable laws of thermodynamic equilibrium.